Okay.
Yeah, it's like relatively like half full. And it was so cold here now that we needed to turn off a little bit the aircon. But outside it's like 35 degrees. So I think here? Yes, they are really brave how they deal with this temperature difference between the aircon and outside. I have to say that I acknowledge everyone here that they are really brave. I could have taken my jacket, but I did not because I did not expect that. We are really happy to have you here, Colin. I'm here with Erica, that you know very well.
Hi, Erica.
We are facing you, but you cannot see us, so we can. Okay. You can come here now and like face everyone. Everyone, welcome to this symposium, the IGCP 732 symposium on the Anthropocene. We have a very special talk now because we have Colin Waters. He was for many years the chair of the Anthropocene Working Group and responsible for, in fact, putting together the proposal to formalize the Anthropocene into the geological time scale that we had like a brief explanation now in the BB's talk there. So everyone is familiarized with these terms. And Colin is going to talk about the geological Anthropocene now for us. So it's really nice to have you here, Colin, the heart of the Brazilian Amazon. And the floor is yours. Thank you very much.
Thank you very much, Juliana. Thank you very much for this invitation to give us a keynote presentation. Sorry I can't be with you in person. But the content of this presentation is, firstly, just to give you a brief introduction. It sounds like you've already had an introduction to what the geological Anthropocene represents. Then to provide the justification for the Anthropocene as an epoch of geological time, so why we don't think we're living in the Holocene anymore. And then, more specifically, why we in the end decided to suggest that the Anthropocene starts in a very specific year, 1952. So this will be the compilation of the evidence from 12 sites that were put forward as proposals as the stratotype for the Anthropocene. And I'll focus in what time we have just on 3 components of this. So it's the nuclear fallout signals, burning of fossil fuels, and biotic change. So many of you are familiar with the origins of the term the Anthropocene. It comes from this gentleman. He's a Nobel laureate atmospheric chemist, Paul Crutzen, who at a conference in 2000 was getting increasingly frustrated by hearing everyone talking about the fact we were living in the Holocene, and stood up and said, no, we're living in the Anthropocene. And he was asked to provide some sort of a definition to this term in this paper, which also came out in 2000, where he said, it seems appropriate to to assign the term Anthropocene to the present, if many ways, human-dominated geological epoch, supplementing the Holocene, the warm period of the past 10 to 12 millennia. At the time, he thought perhaps the onset of the Anthropocene could be in the late 18th century, so during the Industrial Revolution, but then also acknowledged that this was really the responsibility of geologists to make that decision. One perhaps flaw in the article is the title, Geology of Mankind. And similarly, you get a common phrase of the age of humans. These are terms which give this impression that what Paul was talking about is all human impact over all time, when in fact he was very specifically talking about modern, very dominant changes to the planet caused by humans. Probably the second great advance in the science was the realization of something called the Great Acceleration. And this was particularly developed by another colleague, Will Stephan, who produced these great acceleration curves initially in 2007 and again in 2015. And this is the 2015 versions, amended to show current values for the present day. Now, what he realized was that there were a series of socio-economic trends shown here on the left in orange, which more or less consistently showed a prominent upturn around about 1950. And these were drivers for a number of Earth system trends as well, shown in blue on the right-hand side, many of which also showed a marked upturn around about 1950. So it became increasingly apparent to Earth system scientists that perhaps not the Industrial Revolution represented the onset of the Anthropocene, but perhaps the significant change is more around the 1950s. I can't talk about these in any detail over the next 30 minutes, but just to pick out one of them, the population change, it's a significant aspect of the change that we see in the 1950s. So if we go back to the onset of the Holocene, 11,700 years ago, global populations were about 2 million, so a moderately sized city population spread across the entire planet. And that changed gradually over the next few thousand years, to the point at the start of the Industrial Revolution where we had 800 million people. It took 300,000 years to reach a population of 2.5 billion. It only took another 30 years to develop another 2.5 billion to add to that. In fact, now we're at 8.23 billion. So it's fair enough to say that during the Holocene, human impacts are slow and diachronic and have built up over time, but that can't be said for the acceleration that we see in the 1950s, where we've more than tripled human populations. Add to that within that the populations are consuming more, there's more mechanization, industrialization, and global trade, means that the impact of individuals now is much greater than it was in the past. So the Great Acceleration represents this fundamental change to the planet that we've caused. Geologists didn't really get involved in this discussion until as late as 2008 with this paper, Are We Now Living in the Anthropocene?, which was produced by members of the Geological Society of London. The paper was led by Jan Zalazevich. I was one of the minor contributors to this paper, not realizing that I would then spend the next 15 years of my life working on this topic. The paper itself, when you read it, is fairly basic. There's so much more new information that we have now, but the importance of it was that the Subcommission on Quaternary Stratigraphy was interested in this topic and asked Jan to come forward to lead a new working group, the Anthropocene Working Group, to see whether we felt there was a legitimacy to this, that it should be formalized, and if so, when it should start. And that working group started in 2009. If we then fast forward through to 2023, having done our analysis, we submitted the proposal on the 31st of October 2023. If you want to see the contents in its entirety, we then put the proposal into Archive. So if you look under this, the Anthropocene Epoch and Crawfordian Age proposals by the Anthropocene Working Group, it's in 3 parts. So the short executive summary, if you go to file 6853, you'll see the content. If you look at part 1, the Anthropocene series, Epoch, stratigraphic context and justification of the rank, go to file 6954. This represents essentially the next part of my presentation. And then part 2, descriptions of the proposed Crawford Lake global boundary stratotype section and point, and supporting standard auxiliary boundary stratotypes. That's file 6963. That represents the second part of my presentation. But in summary, what we proposed was that the Holocene, which is the last 11,700 years of geological time, ends in 1952 and will be superseded by the Anthropocene. All geological time units have a basic unit of a stage or age. So for the Holocene, there are 3 stages, the Greenlandian, North Grippian, and Megalayan, roughly about 4,000 years in age each, all formally defined. They're named after the type locality. So in our case, if we were to have this defined, the type locality we proposed was at Crawford Lake in Ontario, Canada, so hence the name Crawfordian. However, in March 2024, our proposal was rejected, so delete that. We're still living in the Holocene, and we're still living in the Megalayan. And so the next part of my presentation is to explain why we feel that doesn't make much sense. And this figure in particular hopefully strengthens the message that we're making. If you look at the greenhouse gases, carbon dioxide, methane, nitrous oxide, we have records of this going back 800,000 years in Antarctic ice. We're just looking here at the last 30,000 years of that record, showing the transition from the Pleistocene into the Holocene. And you can see there's this slow, gradual change. So elevations of carbon dioxide, increases in global temperatures happening over about 6,000 years. There's this transition then into the Holocene, which is a remarkably stable, nearly 12,000 years, where not much is happening with regards to greenhouse gases and temperature changes. The most significant change that you see on this figure, hopefully you can see straight away, is what we have here as you transition into the Anthropocene. So in the case of carbon dioxide, atmospheric CO2 levels have increased by 146% against Holocene levels. It's the highest it's been for the last 3 million years, so higher than any time in the Quaternary. Methane levels are even more rapidly, significantly changed, about 257% of Holocene levels, and the highest for at least 800,000 years. And for nitrous oxide, it's 119% of Holocene levels, and again, the highest for at least 800,000 years. The effects of these greenhouse gas emissions on global temperatures, seen in this top figure. Okay, so the rises are probably about 1.5 degrees above pre-industrial levels, the highest in the last 125,000 years. This is a relatively insignificant rise compared with what we see at the Pleistocene-Holocene transition. However, the rate of rise is about an order of magnitude faster than we see at that time. And in the case of carbon dioxide, the rate of rise is probably 2 orders of magnitude faster than this transition. So not only in the case of things like carbon dioxide and methane, that the levels of change are so much more significant than they are at the Pleistocene-Holocene boundary, they're also orders of magnitude faster. If you sort of take a take-home message from this figure, I would say probably, first of all, there's this argument made, a spurious argument, to say that the onset of the Anthropocene, it's diachronous. The human impacts are slow and progressive over time. But diachronaity is something that's embedded in geology, and it's never affected any decision in the past to define a precise chronostratigraphical boundary. So in the case here, we see the Pleistocene transition into the Holocene is taking about 6,000 years. It's slow, progressive, and yet the Holocene working group was able to put a specific boundary, which helps distinguish between the Pleistocene record and the Holocene record. We're doing exactly the same with the Anthropocene. We can argue here that our boundary is much more precise. It's more isochronous than that you see in the Holocene. And the other point to make is that the Holocene is subdivided into these 3 stages, and yet there's practically no significant change to the Earth system during this interval. This represents a fairly stable succession. And yet, we have formally defined stages of the Holocene and the Holocene itself. The one thing that's most prominent on this figure is the one thing that has no recognition on the geological timescale at present. It's the Anthropocene. This to us just doesn't make sense. It's true also for stable isotopes of carbon. So again, a fairly constant succession going right through here into the Holocene, but then the big drop that we see here of 2 parts per mil happening in the Anthropocene, and with stable nitrogen isotopes, a gradual fall over time through into the Holocene, and then the rapid fall that you see of 8 parts per mil again into the Anthropocene. This is important, even though this is actually from ice core, as was the previous information we looked at. These stable isotopes can also be recorded in organic sediments, in carbonates such as corals, in speleothems, and even in tree rings. So here we get signals which you can actually recognize globally. Another point that's often made is, well, the Anthropocene is just a blip. It's only 70 years. It's far too short to be recognized as a geological time interval. Well, we go back again to our CO2 curve that we showed before. This is now for the last 20,000 years, showing this gradual change as we transition from the Pleistocene into the Holocene. So this is CO2, this is global temperatures. We're at this point here where we're rapidly transitioning into this new Earth state. This is showing a series of emission scenarios. Now, geology can only look at the past record. It can't future predict what's going to happen. But that's the sort of the role of climate scientists, and that's what they're doing here. They're saying for a specific emission scenario, in this case, the most conservative one is 1280 billion tons of CO2 emitted into the atmosphere since the Industrial Revolution. We're currently at about 1,100 billion tons. So we're pretty much at this level now. And in the case of the CO2 and global temperatures, you can see that that level represents a significant transition away from the normality of the Holocene. So we've moved into a new Earth state, and that will persist. In this case, the modeling is suggesting for 10,000 years. So that's the same length as the Holocene again, but probably much longer than that. And that's the conservative estimate. So we could be looking at potentially temperatures not of 1.5 degrees above industrial, but more towards 6 to 7 degrees if we carry on emitting at current rates. So really what you're arguing here is that the Holocene isn't necessarily a short interval of time. It can be probably predicted in the case of greenhouse gas emissions and temperatures to be something that would be long lasting. And it's been argued that it's probably delayed the next ice age by a further 120,000 years. So some blip, I would say, and if anything, perhaps in the future, we'll be looking back at the Holocene and saying that's the true blip. But it's not just greenhouse gas emissions and climate that we're talking about here. There's lots of other effects during the Anthropocene, such as sediment loads. This is some work done by Jai Savitsky, also a working group member, looking at sediment loads through time between 1950 and 2010 in billion tons per year, recognizing that there's a threefold increase in soil erosion. That you would think should increase the amount of flux of sediment passing from the land to the sea, but in fact that's decreasing, largely because of the construction of huge dams blocking off sediment supply through river systems into the ocean. There's been a near tenfold increase in trawler fishing, disturbing ocean sediments, particularly most of the continental shelves now are largely disturbed by fishing processes. When you include other factors, which I'll discuss in the next slide, you start to get to a point where there's a 327% change in total sediment load only in 60 years. So during this early part of the Anthropocene, there's a significant change to sediment dynamics on our planet. That additional information calculated a different way, so the figures are slightly different, but it gives you the similar story. This is work by Cooper et al., published in 2018, which looks at various types of artificial deposits, the material deposited by humans onto the planet's surface, breaking it down to different components. First of all, in pale blue, we have mineral and metal production, but importantly also including the waste, the overburden associated with that mineral production. In coal and its waste materials shown in orange, then the cement and aggregate, particularly relevant to the production of concrete, shown in grey, offshore dredging in yellow, and civil engineering works in blue. Combine those all together, and you start to see this classic great acceleration curve to the point where direct human contribution to the global sediment production increased 30-fold between 1950 and 2014. So that's something like 316 billion tons of this sediment being produced, or 150 cubic kilometers in 1 year. It becomes instructive when you then put in that figure we looked at in the previous slide, that this is the flux of sediment from land to ocean. In 1950, looking at that data, you'd say that sort of process far outweighs that of human production of sediment. But unfortunately, you can't say the same today. It's very much a different picture. We also have a host of novel materials and pollutants which can be distinctive of the Anthropocene. So there are about 5,000 naturally occurring minerals. By 2017, it was calculated that there were about 180,000 artificial mineral-like compounds. And today it's more like 300,000, if not exceeding that. So there's a whole host of these novel materials that are suddenly appearing in the geological record. And you present them in this way, where you're looking at where we know where they've been invented and developed, shown in dashed lines, when they go into major production, shown in the black lines. But many of these cluster around about the 1950s, and so can be used as a potential marker when found in sediments. Some of them, like aluminium and Portland cement, these were developed more earlier than the 1950s, but by far and away the majority of their production has been since 1950. So there's these novel materials. There's also things like fly ash particles I'll talk about later. There's DDT, a pesticide, dioxins, PCBs, things like polyborbonated diphenyls. These are flame retardants. These all start to appear again in the 1950s as potential markers, but perhaps the classic one is plastic polymers. So you look at these, other than viscose and bakelite, which comes in a little bit earlier, the majority of these polymers have been developed and go into production around about 1950 or slightly later in the case of the PETs and UPVCs. Because they're globally distributed now, the potential of using plastics is a great one for representing the transition into the Anthropocene. The chemical signals as a whole are relatively complex and often regional or continental in scale. If you look at specific markers such as carbon dioxide and sulfur, they can be produced by things like fossil fuel burning and industrial pollution. Metals such as lead, copper, zinc and mercury, products of both mining and smelting, industrial pollution, fossil fuel burning. PCBs through industrial pollution, radioisotopes from nuclear tests, and then nitrates, methane, and things like these pesticides, DDT, a result of agriculture and deforestation. So there's a whole host of causes of these changes. And if your focus is on when they first develop, the first human development of these changes, yes, they can be very variable, in times over thousands of years. But the fixation on that onset of the signal is not the message that Paul Crutzen was trying to give. It's where you have that fundamental change, where it suddenly increases, it's a great acceleration. And when you start to look at where the signals change abruptly, then they consistently start to cluster again around about the 1950s. Okay, so there's variations of decades here, but that's characteristic of the fact that we're not looking at one cause here. There's lots of different causes for these changes. You wouldn't expect them all to happen exactly in 1950 or 1952. But the message here is that there are so many different signals that have all happened to change around about the same time. Some have peaked in the late 20th century and have subsequently started to decline to the point where they're back to 1950 levels again in some cases. So these represent signals which will be short in duration, admittedly, but they'll represent a permanent marker of the base of the Anthropocene, whereas some of the other signals, like the carbon dioxide, will represent very long duration indicators of the body of the Anthropocene. So going on now to the assessment of the 12 sites, this figure here, each box represents the name of the site, the name of the section, altitude above sea level, the Anthropocene component of the core, and the age it was acquired. Now there's, say, 12 sites in 8 different environments on 5 continents. So the environments include lake sediments here in pale blue. So we've got Crawford Lake in Canada, Searsville in the USA, Sihalongguan in China. We have speleothems here in red, and that's Ernesto Cave in Italy. Marine successions in dark blue. So we've got the East Gotland Basin and Beppu Bay in Japan. Peats, so we have the Snieżka peatland in Poland. Urban sediments in grey, that's Karlsplatz in Vienna. In yellow, we have corals, so we have 2 of those, North Flinders Reef in Australia and the Flower Garden Banks Reef in what we still call the Gulf of Mexico. Then we have in white, ice core from Antarctica, and finally in green, the estuarine successions of San Francisco Bay in America. So what hopefully comes from this is the great diversity environments, but also things like altitude differences, varying from 1,897 meters in the Antarctic through to minus 241 meters in the Baltic Sea, and how great the difference in thicknesses of these successions are, from 4 millimeters in the case of Ernesto Cave through to nearly 35 meters in case of the ice core. So we have here a broad sweep of different environments, different settings, all of which we were trying to find out whether they actually displayed signals of the Anthropocene. The first marker we look at is plutonium, and this is the marker that we considered should represent the primary marker for the onset of the Anthropocene because of its consistency in level. So of the 12 sites, the only one that's missing from here is Ernesto Cave, because the plutonium signal doesn't work its way into the speleothems. hopefully, as a broad pattern, you can see that other than San Francisco Bay, the corals, and Palmer ice core, which is very, very low concentrations, most of the sections show a very distinctive curve, which rises around about 1952, peaks around 1963, and then decreases very rapidly. So change point analysis for 7 of the sites gave an age of 1952.9 as the median. And this just happens to coincide with the first thermonuclear detonation, the Ivy Mike detonation in 1952 on the 1st of November. So there's a very clear linkage between an onset of the plutonium spike at about a time when we have this major change in fallout signals. And that's nicely represented in Crawford Lake, and it's why this site was chosen as our proposed GSSP. So you can see a core here that goes back about 1,000 years. It's got this very fine varved lamination, so it's seasonal changes. If you look closely at them here, you get a pale summer calcite lamina, and then in the autumn you have dieback of diatoms, gives you these darker organic lamina. So the Crawford site analysed each of these varves through plutonium and saw a very dramatic rise in 1952, which again they link to the onset of these thermonuclear detonations. They, in the end, decided to place the GSSP very specifically at the top of the summer lamina, the calcite, because most of the upturn in plutonium occurs actually within the organic layer above, and that specifically represents the fall accumulation, the autumn accumulation in 1952. Again, it's the time when we have the first thermonuclear detonation. So you can be precise here to a fraction of a millimeter, to the point where we say we transition from the Holocene into the Anthropocene. The other bomb spike markers, that includes radiocarbon, shown here in blue, and cesium-137 in red, also show these changes around about the middle of the 20th century, sorry, the 1950s. So other than there are some variations, most of the radiocarbon signals show an increase, not quite as abrupt as we saw with the plutonium, with a peak that's not quite so clear, and it doesn't descend back to current level, to 1950 levels so abruptly either. So it's a much broader curve here. Hopefully, if you look at the change point analysis, you'll see that it has a median value of about 1959. So it's quite a bit later, about 7 years later than the plutonium signal. Good reason for that, because radiocarbon does occur naturally in the environment. Even at peak times, it was just doubling the amount of radiocarbon in the atmosphere. So there's a slow process of building up this radiocarbon. So even in the atmosphere, it doesn't start to rise until about 1955. And of course, there's then a lag between the atmosphere and depositing in lakes and oceans. So as a whole, you get a much more delayed signal for the radiocarbon. The cesium figures, the data you see here, it very much replicates the plutonium. So you get an abrupt change 1952, a peak 1963 for many of the sites. However, some of them also then show much greater concentrations towards the more recent intervals at the core. This probably represents the fact that cesium can be mobile in certain circumstances, and also because you get things like the Chernobyl signal coming here in the 1980s. But overall, the other bomb spike signals sort of endorse the evidence that we saw with the plutonium. And the Snieżka peatlands was a good example where the radiocarbon, plutonium, and cesium was all analysed. The radiocarbon here, we can see the blue squares here match very nicely with the atmospheric concentrations, in large part because there's no delay here. The signal that we see with radiocarbon comes straight from rainwater. There's no passage through into a lake or a marine succession. And the plutonium signal, as we say, very abruptly rises 1952, and then we have this more problematical cesium record here. But this figure also very nicely shows how we're not just looking at radionuclides here. There are lots of other markers that we consider. And in this case, these ones represent the products of burning of fossil fuels. And we see there's quite a close match between the plutonium and the spheroidal carbonaceous particles, then mullite, which is another type of fly of inorganic fly ash, and then the mercury concentrations as well show a prompt increase here. So the next part of the presentation is looking at these products of fossil fuel combustion. Now, again, the driver for this is this increase in energy consumption across the Great Acceleration. So things like coal carries on being burnt at great amounts. However, the significant change in the 1950s is that greater consumption of oil and natural gas, to a point where energy use since 1950 is about 1.6 times greater than in all previous human history. About 90% of all gas, oil, and coal that's been burnt to date has been since 1950. So it's not surprising that the products of this burning of fossil fuels is what we're seeing in sediments in the 1950s onwards. And that's shown very nicely by looking at the spheroidal carbonaceous particles across our sites. And again, we quite often see this prominent upturn happening around about 1952 with a peak, variable age for the peak, and then it tails off again. However, there's much more diachroneity in the signal compared with that we saw with the fallout signals. So in places like Searsville, that increase can happen in the 1930s and 1940s, whereas in Beppu Bay, it's more like the 1960s. So diachroneity of a couple of decades, perhaps, but a broad clustering around the 1950s as that time of transition. So these spheroidal carbonaceous particles, I should point out, they're about 50 microns across here with this very distinctive pitting. So fairly easy to find these within particularly lake and marine successions and in peats as well. And Silhaolangwan Ma was a very good example of looking at the products of this burning of fossil fuels. So again, a core here which stretches back a couple hundred years. This very dramatic colour change, going from more sort of olive green anoxic conditions through into these dark anoxic organic rich successions that you see in the second part of the 20th century. This very nicely resolved annual lamination valves to the point where you can recognize the specific level for the 1952. And looking at the spheroidal carbonaceous particles and polyaromatic hydrocarbons and soot, all of them show this consistent pattern of a rise starting around about 1952, with slight variations being in China. We have a slight eruption here related to the Cultural Revolution, but very clear evidence again of this transition into the Anthropocene. And then finally, looking at biotic change, much is made of the fact that we have loss of biodiversity. We're having extinction of species at levels which are orders of magnitude above that of sort of the background for the last million years, such that in the next 200 years it's predicted that we will be in a position of a global mass extinction. Though we're not there yet, and perhaps what we're seeing more significantly at present is this declining vertebrate populations. So looking at the WWF Zoological Society of London Living Planet Index, they're estimating that there's been a 73% decline in species populations between 1970 and 2020. And that's even more dramatic when you look at Latin America, where it's more like 95% reduction. So we're seeing declining populations, but we're also seeing homogenization of species across the planet. So we're having these introduction of new biotic species. In the top example, it's a transference of species in the ballast water of container ships moving from port to port along trade routes, such that places like the Mediterranean have in excess of 250 introduced species. This work by Siebens et al. Is looking at the recorded first appearances of species over the last 500 years. Interestingly, things like the Columbian exchange that happened in the sort of 1500s doesn't really show any significant increase in the recording of new species. The first major change you're seeing happens from about 1800 onwards. The most part of this is related to introduction of new plant species as Victorian collectors went out and started to bring back to their countries plant species. The next change happens from the 1950s onwards where there's this dramatic increase, more across all species being introduced, across the planet, to the point where about 37% of reported introduced species occur between 1970 and 2014. If we go back to our sites, obviously not all of them will show biostratigraphical markers, but the ones that do, we wouldn't expect that there'd be a consistent marker across these, because we're looking at different environments. We've got estuarine, marine, lake and peat deposits. Each will have their own distinctive species, but it became clear that for each of the sites there are distinctive changes that at least locally provide a means of recognizing the Anthropocene within these sediments. So in the case of Beppu Bay, the first appearance of this dinoflagellate. In the case of Searsville, the first appearance of this ostracod. And in Sniezga, the first appearance of this plant species. But a nice example is the complexity that we see in Crawford Lake, where looking at the diatoms, we see that certain species, particularly planktonic ones, show marked declines through into the 1950s, but at the same time other species of diatoms are showing marked increases. Things like the Astronella formosa being recognizable as something that's affected by warmer temperatures in the latter part of the 20th century across much of North America. But interestingly, the diatoms are showing variations for different reasons, some because of nutrient decline, some because of changes in pH, some because of temperature changes. And then similarly with the chrysophytes, pH and warmer temperatures meant that the species increased after 1952, as similarly as with the chlorophytes because of acidification. Whereas dinoflagellates show this marked decrease prior to 1952 because of nutrient decline. So as a combination, a very complex story, but consistently providing a transition between what we might consider to be Holocene species versus Anthropocene. So in summary, over the last 11,000 years, strata show an increasing but gradual human modification of landscapes and biodiversity. This is what we consider the Holocene to be, is this gradual change. But then there's a substantial, abrupt and globally synchronous physical, chemical, climatic and biological change to the Earth system, which intensified in the mid-20th century, what we're terming the Great Acceleration. This is our preferred start for the Anthropocene. The carbon cycle and global temperatures are likely perturbed outside of Holocene levels for at least 100,000 years, so at least 10 times the duration of the Holocene. The biological changes in many cases are likely permanent. The working group proposal includes data from 12 sites spanning 5 continents and 8 environments. The Anthropocene is clearly discernible in many proxies, with 1952 the optimal start. So with that, I just want to thank, first of all, members of the working group listed here who all contributed to the development of our proposal, and also to members of the Haus der Kultur und der Welt in Berlin, who helped contribute to the funding of the latter analyses, and in particular to those researchers involved in the 12 teams who came up with the final proposal. So many thanks.
Okay, now our microphone is turned on. Sorry about this 30 seconds that we were, because we muted ourselves to not disturb your presentation.
Nice.
Thank you very much, Colin.
Okay.
Nice to hear you. We hear very well. Oh, we have many more people now here in the room that I did not realize. Anyone has a question? I think we have a microphone here. Huh? Anyone would like to ask a question to Colin? Yes, please. You can briefly present yourself, say who you are, where you come from.
Okay. Thank you very much, Dr. Colin. My name is Cesar Martins from the University of São Paulo. Probably it is not an easy question to respond. In the 12 candidate sites to DCSD, they don't consider sites from Africa and South America.
So the sound quality isn't brilliant, but I took that as being, why is there no site in South America?
Yeah, why the 12 candidates sites to dts-uiou-yyd? That's all projections about the South American and African sites.
Right. So
several number of studies describing the Anthropocene in these areas.
Yeah. So geologically, there's no reason. There is no doubt. This is very bad feedback. There's no doubt at all that the records will be equally as well presented in South America. The main reason, to a large extent, is we were suddenly told we had the funding in 2019 to do the work. So we had a 2-year window. So we had to go to already established scientific research bodies who were carrying out this sort of work, who also had to some degree proven that there was going to be a good chance the Anthropocene would be visible. Because what we didn't want to have was a situation where we have 2 years of research and at the end of it, we've picked the wrong sites. And unfortunately, within that very short window of a few months, we had to pick out 12 sites. And most of those are from organizations which are from North America, Europe, and Asia, which is where most of the sort of high-profile science looking at multi-proxy analysis, because we couldn't look at just one particular signal. We had to look at a whole host of them. And these already had the labs set up to do this sort of work. Now, I was keen to get from Africa and South America potential collaborators. And in fact, in 2019, I was speaking to people in Chile with the possibility of using tree rings, because that's the one environment we didn't look at in this study was tree rings, and the potential for doing it in South America. Unfortunately, we just couldn't find any team who were able to pick this up in time for 2020. But I'm sure if we were to do it again now, we'd have no problems.
Can I quickly add something, maybe, because I am from South America and I was there, participate in these studies. Because I'm based in Germany now, was for us a straightforward tree study the Baltic Sea. So the Baltic Sea is in this map. And we really tried a lot. This was starting in 2020, was, as we know, the beginning of the pandemic. So I'm sorry to use this word, but was quite unfortunate because there was before, right, calling 10 years of research that was made extensively by the Anthropocene group, like studying the literature. So when we started, in fact, to have the money and we could do some analysis, like ourselves to start that, was this site that they were convenient at the moment and that we had direct access, let's say. That's why. And after, I'm not sure, but in the last 5 years, there was other colleagues from the Anthropocene working group, including Simon Turner, that was with calling the secretary when the proposal was submitted, and now he's still the secretary here, that analyzes some other places in Africa. And this became also a publication, showing that we were looking at these places, but because of logistics and convenience, these were the sites that were more studied like in more days. But it's always a frequent question that we hear, right? Yes. Yes, please. Just a minute that will be. Oh.
Thanks, Wallace, for your presentation. I have 2 questions. I'm Pedro. I'm a geologist from Universidade Federal do Pará, North Brazil. I have 2 questions. Why geologists attacked the declaration of Anthropocene last year? And the second one is, what is the better place to collect cores to understand the transitions between Holocene and Anthropocene? Mainly because of the sedimentation rates.
Juliana, can I ask, could you just summarize it. I can't hear on that microphone, but I can hear you.
Okay. I will repeat the questions then.
Yeah.
Pedro
Do the first question, and I'll do them separately then.
Pedro is from the University, Federal University of Pará. He asked 2 questions.
Yeah.
The first one was why the Anthropocene was rejected.
Oh yeah. Okay.
CS and UGS. And the second one is where is ideal to look for pores when you want to see the transition between the scene and the Anthropocene, and he's especially interested in the sedimentation rates in this context.
Right. Okay. So the reason for rejection is a difficult one because the voting members didn't actually provide a feedback, which they normally should do. When they vote, they should say why they rejected it. They should also provide feedback to allow us to modify, to make a resubmission in the future. You know, we need guidance on this. None of that information was provided. We had a summary from IUGS that, as I mentioned in my presentation, said human impact is diachronous, so we can't do it, knowing fully well that all geological boundaries are diachronous, pretty much to a large extent. So if you applied their criteria, then they also deny that the Holocene exists, which clearly they don't say that. And again, they also said it's far too short. And again, there's no rule in chronostratigraphy to say what the minimum duration of an epoch or an age should be. And in the case of the Anthropocene, the changes are so significant that we feel that even though it's only 70 years, that it's still justified. So that's the best we have as far as rejections go. Certainly, we never received any comments back with regard to the submission itself. So the proposal about the GSSP at Crawford and the SABS sites as well, we never had any feedback at all to say what they disliked about them. So we can't build upon that proposal without that guidance. As far as the preferred sites, in the end, the sites that were more supported were those that had these VARVs, so the annual increments of sedimentation, because they allowed us to be very specific to the year on the age. So when they were doing the analyses, they could say this plutonium analysis is specifically from 1 year, which allowed us then to be able to say that we could see physically the changes happening and relate them to known observed effects and say that there's no diachronates, no gradual lag in signals. They happen as and when things like the detonation of the thermonuclear devices happened. That was becoming embedded in the sediments immediately. So sedimentation rates broadly are increasing with time as well, and so that helps, because what we're having then is a thicker development of the Anthropocene. So in the case of some of the sites, we're talking about only a few tens of centimeters in thickness. It's better if we could have greater thicknesses, but at the same time, that can also dilute some of the signals. So things like the plutonium signal could become diluted by having thicker accumulation each year. So there's sort of swings and roundabouts as to the pros and cons, but generally, areas that are undisturbed by human activity and also by biological activity is vital, because what we can't afford to have is a mixing of the sediment record. So does that answer the question?
Later about that. During the day, they had fact that I think it's a very question that we hear often about the rejection of the Anthropocene. And as Colin said, even for us, it's difficult to put like one reason, because we did not hear an official communication from them so far. But it's quite interesting as an exercise to see the New York Times and the Los Angeles Times at that time, like March 2024, how these media, they were reporting the official rejection of the Anthropocene, even before the Anthropocene was receiving like a formal notification, official notification about them. So it's an exercise that you can do also to see how the views were spread around the world. As you're going to see the justifications are all in my point of view, which I cannot go really deep on it. Is there any other question to calling? No? Okay, so I would say we were very successful. Calling, I can brief now. I can also start because it was really successful. Thank you very much.
Thank you. Goodbye.
Yes, goodbye. See you soon. Bye. Yes, and we have. Are we on time? I'm a little bit. 10:30. What do you think? Yes. Yes, should be starting now. Continuar. Eu não tinha contado o próprio banho aqui da tarde. Yes, okay, so I just hear here. Michael, oi, sorry. Hello, can you hear us? You can
Yes, yes, I hear you.
Good, we can see you. Can he see us a little bit? Yes.
Yep.
Look, we are here. There.
Okay.
Hello. Turn on for you. Thank you very much for being here. I see you are here from the beginning. Unfortunately, like Bibi's talk was not yet live in YouTube, but we are now. I also take the chance to say hello to everyone that is with us in YouTube. I always want to say that. So that's cool. We can start with your presentation.
So I will try to share my screen.
Yeah, we are going to do this exercise to see if you can share your presentation with us, or if it would be straightforward to us to present the slides for you. So we can do this exercise now.
Yeah, I tried it. It should be up.
Oh, yes, that's excellent. Good. Yes. So thank you very much for being here. I hope you saw like a picture of the auditorium that we have here. We have a relatively big auditorium here that is like for 50 to 100 persons, and it's at the moment like half full. We are here from, I mean, I would say at least 5 different countries, mostly from Brazil, but we have our colleagues from Poland. We have Yamal that you know very well from Indonesia. We have Bibi that you also know very well. And I think then we are mostly here Brazilians. We are in the heart of the Amazon. The Amazon River is just a few kilometers from here. So it's really nice as a Brazilian, I have to say, to be here. And I just realized that we did not count with the coffee break from the conference when we put together our program. So we are going to hear your presentation now, and then we are going to do a break. I hope it's okay for everyone that is online, but for us here it's also important to go out, have a break, and drink some water, because outside is like 35 degrees. So for everyone that is also here, our presentations then will be, I think, delayed for 15 minutes, that we have the chance to get a coffee outside there. I'm sorry about that. I did not think about the coffee break when putting the program together. So, Michael, and of course, everyone, it's a really nice opportunity to have Michael here with us he is the PI, like he's the reason why we are here now. He's the PI of the IGCP 732 project, together with other researchers, as you all saw in the previous presentation. He's in Austria at the moment, and we are going to hear now talk about his work as a zoologist, not exactly as a part of the IGCP 732 project. I am right? Thank you, Michelle.
So thanks for the possibility to give an online presentation here and to join you at the IGCP meeting there. Unfortunately, I cannot come to Brazil, and just one answer to a question before, why about the global south, about South America and Africa not being within the 12 sites. That's one of the reasons why we got this IGCP project. So I will talk about pretty much the same markers, events, and spikes as Colin did. Okay. I'm not sure how I can move on with my slides. I'm trying the tab, but it doesn't work.
Are you in presentation mode?
I'm in presentation mode, yes. And I'm trying the arrow keys. I'm trying the tabulator key.
Right, you can try. You can use a shortcut from your keyboard to change, to switch between the screens, because to present your next slide, you need to do that in the PowerPoint file. I'm sorry, not in the Google Meet screen. That's the exercise that we did yesterday, and was also new for me. So I learned that yesterday. You can try to minimize this screen, the one that you are seeing now from the meeting, and go without doing anything in this screen, but go then to the PowerPoint presentation, and then you can switch between slides there.
Okay,
yes.
But did it work?
It worked. Thank you very much.
Okay, fine. What are the anthropogenic fingerprints that we have? You already heard that by Colin. So it's some kind of repetition, but maybe some were late for Colin's talk. We have at first and as primary marker these artificial radiogenic nuclides, the bomb spike, as you can call it, in correlation to the golden spikes of the GSSP. So this is the global fallout from atmospheric bomb testing, and it includes carbon, it includes cesium, plutonium, neptunium, iodine, all those, well, more or less artificial radionuclides. Then we have elemental geochemistry. I will show something on that. Stable isotope geochemistry. You already heard about carbon, oxygen, and nitrogen stable isotopes, lead isotopes too. Then we have the technofossils, also archaeological artifacts and artificial rocks, ceramics, plastics, clay bricks, slag, and later on, those were the early ones, later on concrete, plastics, pure aluminium, and so on. Something like called microtechnofossils. You have already heard about the spheroidal carbonaceous particles, SCPs, black carbon microplastics, glass and metal melt microspheres, and finally the biological and paleontological markers. A little bit about the bomb spike of this atmospheric testing with the PSSP proposal that you already heard, starting with the first thermonuclear, the hydrogen bomb detonation test, Ivy Mike on Eniwetok Island, Pacific. It blew away the whole island, the cratering. And I have here some of those radionuclides, the isotopes that were brought more or less into the atmosphere and then came down as a global fallout. And I ranked them by the duration of the half-time, the half-life of those artificial radiogenic nuclides. So they are short ones, like lead 210, cesium 137. They have half-lives of years, 22, 30 years, something like that. Some of them are also a little bit mobile in the rock record or the stratal archive. Then there are americium and carbon C14 with several hundred and several thousand years of half-time. Then we come to the plutonium. Actually, plutonium-239 is the one isotope that has the one plutonium isotopes that has the longest half-time, half-life of 24,000 years. And it's also relatively conservative within the stratal archive. There are several uranium isotopes, but they are more mobile in the stratal record. The one that I will point now is neptunium, neptunium-237, which has a very similar behavior like the plutonium-239. And with accelerator mass spectrometry, you can, well, not easily, but you can measure concentrations in atoms per gram, both of plutonium and neptunium. And the good thing with the neptunium is it has a half-time of 2.1 million years. So it's really a geological marker because some of the, well, let's say, criticism on the proposal of the GSSP and the primary marker using plutonium was the short, relatively short, geologically spoken, short half-time of plutonium with maximum 24 kiloyears. Neptunium is has a longer geological half-time, and that's why we tried within the project here in Vienna to measure both plutonium and neptunium in natural archives to see if they correlate. Then there is iodine, also with a even longer million-year, 15, 16 million-year half-time, but it seems to be more mobile in soils than expected. So those are artificial radiogenic nuclides that we can use to get this bomb spike into our sections. And this is just to demonstrate here on the right side that we have a record of flood sediments of the Danube River here in Vienna or near Vienna. We have a cesium record. These are the data by Diana Hatzenbühler in preparation or in submission, actually. There's a cesium record. There is a pretty plutonium-239 record measured with accelerator mass spectrometry here in Vienna. And there is a neptunium record. And if you look on both those curves, they have, well, it's a flood record. So we have the dating by the floods of 1954, where both plutonium and neptunium show pretty the same behavior up to the global fallout maximum around 1963, 1964. Cesium is already diminishing or even tailing out. But what we see with the cesium record here in this floodplain is the Chernobyl spike. With the plutonium and neptunium, the Chernobyl spike is really minimal in that case. And also the uranium isotope ratios show a very minor peak here. Let's go to the next one that I want to propose, and you already heard about the carbon stable isotopes. They are, because of the SUS effect of the fossil fuel burning, they go to the decline within the records, and we see that in the peatland in Poland, a very clear record of this decline in the delta C13. Of course, oxygen isotopes would give some information on climate, temperatures, marine sea surface temperatures, maybe nitrogen isotopes and lead stable isotopes are also means for markers for the Anthropocene. Elemental geochemistry, this is a little bit different. They are those typical early elements, metals that were mined and used excessively already in the 19th century, lead, copper, zinc, but also very early in, well, the Iron Age. Of course, there are minor peaks of those elements, of those metals. Very conspicuous is this peak in the youngest. So we have here 1,000 years for now, and here we see this extreme peak of the gasoline, the lead gasoline peak, or the leaded gasoline event, you may call it, that the concentrations of lead and also the elemental ratios to conservative elements like scandium goes up like crazy and comes back because leaded gasoline was banned in the 1970s to 1980s. There are other anthropogenic trace metals, germanium, gallium, rare earth elements, critical minerals at the moment, which are needed for a lot of things, including battery, storage of electricity, and so on. New anthropogenic minerals, and of course there are organic pollutants that are also markers for the Anthropocene. Technofossils, like macro technofossils like ceramics used for dating in archaeology for a longer time. plastics, bricks, metal slags, and for the Anthropocene, of course, the plastics and concrete. We have already heard about that. Also spheroidal carbonaceous particles, but there are also new compounds and new mixed rocks, like the plastic agglomerates, typical for beach sediments, beach rock, and burned plastic on beaches, which builds the matrix of conglomerates. Biological paleontological markers, I don't want to go into details, the time is running, but the accelerated extinction in vertebrates here, as you see, and the biomass changes with livestock and pets. Most of the biomass of bigger animals today on the planet, Columbian exchange, invasive species, and the sixth mass extinction that may go on within the next few hundred years. The Great Acceleration event, you have already heard about that. Just to remember Will Steffen, who really was the driver of this term on the Great Acceleration, who died recently and was also a member of the Anthropocene Working Group. This was already presented. Just one recent study or two recent studies, but one is more important because it not only included the proxy data, the anthropogenic fingerprints by the Anthropocene Working Group, but a lot of other sections you see here, not the 12 ones that we had data on, but here a lot of others. Kuwai et al. 2024 were working on that, and they came to a change point. Here is the maximum around 1952 of changes, of proxy changes, and this is the change point analysis that comes up again with this 1952 date. So this is more or less outside from the Anthropocene Working Group, using a lot of other sections that were already published by that time and where data was available, and they came to the same result of 1952 as the main change due to this great acceleration, which is also fingerprinting into the proxies that have an anthropogenic relation. And the final question was then, what will future geologic stratigraphers use as boundary markers of the Anthropocene? An interesting, very academic question, of course. Maybe those are alien geologists that come to the Earth and look what happened. The short scenario, the short time scenario in the next 100 up to 10,000 of years, that's something that the Anthropocene Working Group was already working on. So there is the bump test spike, but I really wonder if there will be within this century also a separate potential nuclear war spike. The world is not the best one, as we see today. So radionuclides like plutonium, fly ash, spheroidal carbonaceous particles, delta C13, negative carbon isotope SUS event, and the leaded gasoline event. Those are, and the climate event, of course, with the climate warming. So that's something for the next hundreds, thousands of years. But if you look on a million-year scale, so this is 15 million years, and you have 23 million years. I think the Neptunium will be the main conservative, stable signal of this fallout or nuclear spike or nuclear spikes that humans produce and hopefully not will produce in future. Then the fly ash spike, I think the STPs will not be so stable. But of course, we have Delta C13 peaks, excursions in the rock record down into the Precambrian. So this negative carbon isotope event, that will be visible also for the future geologists, whoever that is. So with that and the conclusions, I hand over, and I'm happy to answer questions on my content. Thanks for listening.
Thank you very much. Sorry for the second, because we use our microphone and then we are now again on. We will have time for one question, because then we are going to need to move ourselves here for our coffee break, Michelle. And if you can then, oh, you can see it there. Here. I can sit here then. Yeah, yes, I can see it.
Okay.
Yes, yes, there are questions here. Just a minute.
Oh, I'm just waving, sorry.
Okay, everyone is saying hi here to you. Do you have a question? David, have you seen that he also mentioned your last question from before? That the IGCP project is used for that? Yeah, okay, immediately I don't see any questions. I think we were very fortunate to have your presentation just after Colin's presentation, because we had like a kind of review of the proposing concept, that like the way that we went until the proposal, and now like these highlights of the markers. That is very nice and very important. We also did a little bit of that in our workshop on Sunday, but not everyone was there. So good that now we had this global overview. Okay, thank you very much. Michelle, if you can stay 1 minute more that I want you to you, I will say here to everyone that thank you very much for being here in this first part. We are going to have a 15 minutes break now that we can join everyone in the coffee break. And I would like everyone to be here back at 11:15, that we are not later in our thank you very much. See you soon. For those that are in YouTube, we are also going to do a 15 minutes break and we are going to be back. So please stay on. Yes. Michelle, deixa eu falar com o Michelle só um minutinho. Yes, go. Yes, vai e já. Vê se você consegue colocar os posters e tomar um café também. Michelle, I think we are, I did consider the coffee break when we were organizing the presentations, but the coffee break here was later.